Learning goals. Welcome to this learning session on kinetic theory and the states of matter. In this course, we shall address kinetic theory and particle behavior, states of matter and phase transitions, fundamental gas laws, gas diffusion and partial pressures, ideal and real gas behavior. There will be a quiz at the end to test your knowledge.
Introduction to Kinetic Theory. Welcome to the kinetic theory of matter, a fundamental concept in chemistry that explains the behavior of different states of matter. This theory is based on the idea that all matter is composed of tiny particles, molecules, atoms, or ions, that are in constant, random motion. In this section, we will focus on understanding and applying the kinetic theory, particularly how particles behave in gases. We will also explore how gases are prepared in laboratory and their practical uses in everyday life, from industrial processes to medical applications. By the end of this section, you will be able to explain the kinetic theory of matter and distinguish between the properties of solids, liquids, and gases. You will also perform calculations involving various gas laws and analyze related graphs. Fundamental particles of matter. Particles are the small constituent units of matter, which can be atoms, molecules, or ions. These fundamental building blocks determine the physical and chemical properties of substances. Intermolecular forces are the attractive or repulsive forces that exist between these particles. These forces are crucial in determining the state of matter and its physical properties, such as boiling point and viscosity. For instance, water's relatively high boiling point is due to strong hydrogen bonds, a type of intermolecular force. Particle motion, diffusion and Brownian motion. Diffusion is the process where particles spread out from an area of higher concentration to an area of lower concentration. This spontaneous movement continues until the particles are evenly distributed throughout the available space. A common example is the scent of perfume spreading across a room. Brownian motion refers to the random, erratic movement of particles suspended in a fluid, liquid, or gas, resulting from collisions with the fast-moving molecules of the fluid. This phenomenon provides direct evidence for the existence of atoms and molecules and their constant motion, first observed by Robert Brown in 1827, while studying pollen grains in water. Gas laws and standard conditions. A gas law describes a mathematical relationship between the pressure, volume, temperature, and quantity of a gas. These laws are fundamental to understanding how gases behave under varying conditions. Mole fraction is the ratio of the number of moles of a specific component to the total number of moles in a mixture. This concept is particularly useful in analyzing gas mixtures, such as in atmospheric chemistry, where the mole fraction of oxygen is approximately 0.21. Standard temperature and pressure (STP) are defined as 0 degrees Celsius, 273.5 K, and 1 atom in pressure. These conditions provide a reference point for comparing gas properties, and at STP, 1 mole of any ideal gas occupies 22.4 liters. The kinetic theory of matter explains the behavior of matter based on the motion of its constituent particles. These postulates are fundamental to understanding the states of matter. The kinetic theory of matter is built upon several key postulates. Firstly, matter is made of tiny particles, which are in constant random motion. This continuous movement is what gives particles their kinetic energy. Secondly, matter possesses kinetic energy due to the motion of these particles. The average kinetic energy of the particles is directly proportional to the absolute temperature of the substance. This means hotter substances have faster moving particles. Finally, the difference between the different states of matter is primarily due to the nature and extent of motion, as well as the separation between the particles. These factors dictate whether a substance exists as a solid, liquid, or gas. Solid state, properties, and model solids exhibit distinct properties due to the arrangement and interaction of their particles. They have a fixed shape and volume at a given temperature, unlike liquids or gases. This rigidity is a defining characteristic. Particles in solids are closely packed in an orderly, regular manner, forming a crystal lattice in many cases. The forces of attraction between these particles are the strongest among the three states of matter, significantly outweighing the kinetic energy possessed by the particles. These strong forces hold particles in fixed positions, allowing them only to vibrate about their mean positions. Increasing the temperature of a solid causes these particles to vibrate faster, increasing their kinetic energy, which can eventually lead to melting. Liquid state, properties and model liquids possess unique properties, including a fixed volume but no fixed shape, meaning they take the shape of their container at a given temperature. This characteristic is essential for many everyday applications, from beverages to hydraulic systems. The particles in liquids are close together but arranged randomly, allowing them to move rapidly and slide past each other in all directions. While the forces of attraction between liquid particles are stronger than those in gases, they are weaker than in solids, enabling this fluidity. Liquids are not easily compressed due to the minimal empty space between particles, similar to solids. However, they expand on heating as particles gain kinetic energy and move further apart, though intermolecular forces remain constant. Visualizing solid and liquid states. Understanding the arrangement and motion of particles is key to distinguishing between solids and liquids. In solids, particles are tightly packed and vibrate in fixed positions, maintaining a rigid structure. For example, ice molecules are locked into a crystalline lattice. In contrast, liquid particles are close together but randomly arranged, allowing them to slide past each other. This freedom of movement enables liquids to flow and take the shape of their container, as seen with water molecules moving past one another. Changes of state, melting and freezing. Melting is the process where a solid transforms into a liquid upon heating. When solids are heated, their particles gain kinetic energy and vibrate more strongly. As this energy increases, the attractive forces between particles weaken in comparison to the particles' kinetic energy, allowing them to break free from their fixed positions and move around. Freezing is the reverse process, where a liquid transforms into a solid upon cooling. When liquids are cooled, their particles lose kinetic energy. This reduction in energy allows the attractive forces between particles to strengthen, restricting them to fixed positions. Although particles still move, their motion is now limited to vibrations within a fixed structure. Changes of state, evaporation and condensation. Evaporation occurs when particles of a liquid escape from the surface to form a vapor. On heating, surface particles gain sufficient kinetic energy to overcome intermolecular forces and move into the gaseous phase. This process can happen at any temperature below the boiling point. Boiling is a rapid form of vaporization that occurs throughout the bulk liquid at a specific fixed temperature, known as the boiling point. Unlike evaporation, boiling involves the formation of bubbles of vapor within the liquid itself. For water, the boiling point at standard atmospheric pressure is 100 degrees Celsius. Condensation is the change of state from a gaseous form into a liquid form. This happens when the temperature of the gas is lowered, causing its particles to lose enough kinetic energy to form bonds and transition back into a liquid. Condensation is the reverse process of vaporization, crucial in phenomena like cloud formation. Phase changes diagram matter can transition between solid, liquid, and gaseous states through various phase changes. These transitions are driven by changes in temperature and pressure, which affect the kinetic energy and intermolecular forces between particles. The diagram illustrates the 6 primary phase changes: melting, solid to liquid; freezing, liquid to solid; evaporation, liquid to gas; condensation, gas to liquid; sublimation, solid to gas; and deposition, gas to solid. Each process involves either the absorption or release of energy. Introduction to gas laws. Gas laws are empirical relationships that describe how gases behave under different conditions, relating pressure, volume, temperature, and the amount of gas. These laws are crucial for predicting gas behavior in various scientific and industrial applications. Understanding these laws has practical applications across many fields, including engineering, chemistry, and physics. For example, the design of internal combustion engines relies heavily on the principles of gas laws to optimize fuel efficiency and power output. We will explore individual gas laws, such as Boyle's, Charles's, and Gay-Lussac's laws, and then see how they combine into the ideal gas equation. These principles form the bedrock of thermodynamics and physical chemistry.
Boyle's law. Pressure-volume relationship. Boyle's law states that for a fixed mass of gas at constant temperature, the volume of the gas is inversely proportional to its pressure. This means if you increase the pressure on a gas, its volume will decrease proportionally, and vice versa. This principle is evident when you squeeze a balloon.
Mathematically, Boyle's law is expressed as P1V1 equals P2V2, where P1 and V1 are the initial pressure and volume, and P2 and V2 are the final pressure and volume. This relationship holds true as long as the temperature and the amount of gas remain constant. Graphically, Boyle's law can be represented in several ways. A plot of pressure versus volume yields a hyperbola, while a plot of pressure versus the inverse of volume, 1V, results in a straight line passing through the origin, demonstrating the inverse proportionality.
Charles' law. Volume-temperature relationship. Charles' law states that the volume of a fixed mass of gas at constant pressure is directly proportional to its absolute temperature. This means that as the temperature of a gas increases, its volume will expand proportionally, assuming the pressure remains constant. This principle is why hot air balloons rise.
Mathematically, Charles' law is represented as V1 T1 equals V2 T2, where V1 and T1 are the initial volume and absolute temperature, and V2 and T2 are the final volume and absolute temperature. It is crucial that temperature is always converted to Kelvin for these calculations, as the law is based on absolute temperature. Graphically, Charles' law shows a linear relationship between volume and absolute temperature. When plotted, the line extrapolates to zero volume at absolute zero, minus 273.15 to resource K, a theoretical temperature where all particle motion ceases.
Gay-Lussac's law and combined gas law. Gay-Lussac's law states that for a fixed mass of gas at constant volume, the pressure of that gas is directly proportional to its absolute temperature. This means that as temperature increases, the gas particles move faster and collide with the container walls more frequently and forcefully, leading to an increase in pressure. This is why aerosol cans warn against heating.
Mathematically, Gay-Lussac's law is expressed as P1 T1 equals P2 T2, where P1 and T1 are the initial pressure and absolute temperature, and P2 and T2 are the final pressure and absolute temperature. Again, temperatures must always be in Kelvin for accurate calculations. The combined gas law integrates Boyle's, Charles, and Gay-Lussac's laws into a single equation. P in V in T equals P2V2 T2. This law is incredibly useful as it allows for calculations involving changes in pressure, volume, and temperature simultaneously, provided the amount of gas remains constant. It's a powerful tool for predicting gas behavior under varying conditions.
Avogadro's law. Volume-mole relationship. Avogadro's law states that equal volumes of all gases at the same temperature and pressure contain the same number of molecules or moles of gas. This means that the volume of a gas is directly proportional to the number of moles of gas present, assuming constant temperature and pressure. This explains why a balloon inflates when more air is added.
Mathematically, Avogadro's law is expressed as Vn equals K, where V is the volume occupied by the gas, N is the number of moles of the gas, and K is a constant of proportionality. This relationship highlights that the identity of the gas does not matter, only the number of particles. A practical application of Avogadro's law is in stoichiometry, particularly when dealing with gaseous reactants and products. For example, in the reaction 2H2G plus OG, 2H2OG, 2 volumes of hydrogen react with 1 volume of oxygen to produce 2 volumes of water vapor, reflecting the mole ratios.
Diffusion and effusion. Graham's law. Diffusion is the net movement of molecules from a region of higher concentration to a region of lower concentration due to their random motion. This process occurs in gases, liquids, and even solids, and does not require a physical boundary. A familiar example is the spreading of an odor.
Effusion is a specific type of diffusion that refers to the escape of gaseous molecules through a tiny hole into a vacuum or a region of lower pressure. It is essentially diffusion through a very small opening. Both diffusion and effusion rates are influenced by the molecular properties of the gas. Graham's law of diffusion, or effusion, states that the rate of diffusion or effusion for a gas is inversely proportional to the square root of its density, or molar mass, at constant temperature and pressure. This means lighter gases diffuse and effuse faster than heavier gases. For example, hydrogen gas, 2 grains per mole, diffuses much faster than oxygen gas, 32 grains per mole. Dalton's law of partial pressures describes the behavior of gas mixtures. It's crucial for understanding the pressure exerted by each gas in a mixture. Dalton's law of partial pressures states that in a mixture of non-reacting gases, the total pressure exerted is equal to the sum of the partial pressures of the individual gases at constant temperature. The partial pressure of a gas in a mixture is the pressure it would exert if it alone occupied the same volume at the same temperature. This law is fundamental for understanding gas mixtures, such as the air we breathe. Mathematically, for a mixture of gases 1 and 2, Pt equals Pm plus P2, where Pt is the total pressure and P1 and P2 are the partial pressures of gases 1 and 2. The partial pressure of a gas can also be calculated using its mole fraction. P equals xpt, where x1 is the mole fraction of gas 1, Nn plus N2, and Pt is the total pressure. This relationship is widely used in fields like diving, where understanding the partial pressures of oxygen and nitrogen is critical to prevent decompression sickness. Ideal gas equation, PV equals nRT. The ideal gas equation, also known as the ideal gas law, is a fundamental equation in chemistry that describes the behavior of gases under certain conditions. It combines Boyle's law, Charles's law, and Avogadro's law into a single, powerful relationship. The equation is expressed as PV equals nRT, where P is pressure pascals, V is volume m, N is the number of moles, T is temperature Kelvin, and R is the ideal gas constant. The value of R varies depending on the units used for pressure and volume, such as 8.314 J mol moles km units in SI units, or 0.R82057 atone kming. It is crucial to always match the units of pressure, volume, number of moles, and temperature with the specific units of R being used in calculations. This consistency ensures accurate predictions of gas behavior in various chemical reactions and industrial processes, from calculating gas volumes in airbags to designing chemical reactors. Real gases, deviations from ideal behavior. The ideal gas law is a simplified model that works well for predicting gas behavior under a wide range of conditions, but it fails under extreme conditions such as very high pressures or very low temperatures. In these situations, real gases deviate significantly from ideal behavior. Real gases deviate from ideal behavior primarily because the assumptions of the ideal gas law, that particles have zero volume and no intermolecular forces, do not hold true. At high pressures, the actual volume of gas molecules becomes significant compared to the container volume, leading to a larger observed volume than predicted. At low temperatures, the kinetic energy of molecules decreases, allowing intermolecular forces to become more significant. These attractive forces pull molecules closer together, reducing the pressure exerted on the container walls and resulting in a lower observed pressure than predicted by the ideal gas law. More polar gases, like ammonia, show greater deviations due to stronger intermolecular forces.
Summary. Well done, you have completed the course Kinetic Theory and the States of Matter. You should now be familiar with kinetic theory and particle behavior, states of matter and phase transitions, fundamental gas laws, gas diffusion and partial pressures, ideal and real gas behavior. Should you need to revisit any of the topics in this course, please use the menu at the bottom of the screen.